Welcome back, everyone. In this video, I'll be going over the lecture for the average value of a function. And this is an important topic because typically when we're talking about finding the average or the mean of some numbers, you have finitely many numbers. But if you have something that's representing a continuous curves, for example, temperature over the course of a day, and you wanted to know the average temperature over the course of a day, you have a temperature reading at every single second, at every single millisecond of the day. There's infinitely many of them. Well, computing the average of finitely many numbers is a relatively simple task. You add them up, you divide by the amount of numbers you have, and then that's it. Well, when you want to figure out, let's say, like I was describing, the average temperature over the course of a day, you have to do quite a bit more because you're actually adding up infinitely many numbers, like I said. And probably, once again, not unexpected, is that when we find the average of infinitely many numbers, where those numbers are represented by a function, f of x or something, there's going to be a definite integral involved. So it's not unexpected. In order to compute the average of infinitely many numbers, specifically the average value of a function f on the interval a to b, it will turn into a definite integral. And the easiest way to see this is we begin by approximation rectangles like we always do, but we do it in a different way. Because what we're interested in doing is we're interested in figuring out the average value of a function. So we want to add up f of x1, f of x2, basically plug in all the x values we can, and then divide by the number of them. Well, in this example, I just have 4 rectangles drawn, so that would be 4 x values that we're plugging in, and we would want to divide by 4. But we're not interested in the area necessarily in this problem because we're not interested in, what is the total area? What do we add up? We want to know what this is. What is the average? The idea is to replace our typical our typical b minus a over n with something else. And we've used this a couple times before by saying, well, we don't really want to say b minus over n over and over again, so we say delta x. But the idea is now, because we actually have that n in our formula, replace it with delta x. And we can't replace it directly because if delta x equals b minus a over n, you solve that for n and you get n equals b minus a over delta x. So what we do is we take the average formula here for finitely many numbers, and we replace the n with our b minus a over x. So I'm going to go ahead and just write that down. So we're adding up our n values, and now we're dividing by, instead of n, it's b minus a over delta x. Now the reason why this is so helpful is if you do keep change flip here, so you can bring the delta x to the top as multiplication and the b minus a stays on the bottom, then we get all these f of x values. And then it's multiplied by the delta x from keep change flip. And then we're still divided by b minus a. So this is still the same exact formula that we started with. We're just representing the n being equal to b minus a over delta x, which it is, because that's just rearranging our formula that we're used to. Now, when you let n go to infinity, what happens? What happens when you let n go to infinity? So it's not obvious because there's really not an n here. It's just the number of, x values we're plugging in. But if we do the limit as n goes to infinity of our formula at the end here, now keep in mind, we can represent this as a sum because we're summing up f of x values. So this is f of xi, I equals 1 to n. We have delta x, multiplying it, and we have it all over b minus a. Well, what you want to notice is that our typical Riemann sum is just the sum of this. The b minus a typically is not there. Well, luckily for us, b minus a, it doesn't have an I in it, so we can bring it out. It also doesn't have an n in it, so we can bring it out of the limit as well. That's our property of limits from way, way back when. And it says that we can completely bring it out. So we get 1 minus b over a, then we do the limit as n goes to infinity of the sum from I equals 1 to n of f of xi times delta x. You don't want to plug in back what delta x is. Technically, you could plug in delta x equals this. What we really want to do is say, now this limit of this sum is actually our Riemann sum. It's our typical definite integral. So we have 1 over b minus a in front, and then we integrate from a to b of f of x dx. This is just our typical integral. All right, so what this is saying is that in order to figure out the average value of a function, you just integrate the function from a to b, and then you divide by the length of the interval, which is b minus a. And it really isn't, any more than that. So we don't really think about finding the areas. We think about just using the areas as a reference point for understanding where this n and the delta x and b minus a actually come from. All right, so with that, let's go ahead and jump in. In order to figure out the average value of a function, you're going to have to be given the function itself and some type of interval. But it's not going to be more complicated than as soon as you set it up, you're going to have your integration techniques that you've learned, and you'll use one of them. So this first one, we want to find the average value of the functions. F of x equals 3x squared plus 4x. Always put our dx there, from -1 to 4. So if we were just finding the definite integral, we would be given this, but with the average value, I want to multiply by 1 over b minus a, 1 over 4 minus -1. Now 1 over 4 minus -1, that's 1 over 5. Can you integrate this right away? And your answer should be yes. We have just powers of x's. We don't have anything to substitute or anything like that. So it's just 1 over 5. We integrate 3x squared. We get 3x cubed over 3, which is x cubed, plus integrate 4x. That gives us 4x squared over 2, which is 2x squared. And we plug in from -1 to 4. And so we've got 1 over 5. We want to plug in x equals 4. Then we want to subtract and plug in x equals -1. All right, so x equals 4, we get 4 cubed plus 2 times 4 squared. Then minus x equals -1, we get -1 cubed plus 2 times -1 squared. And then we got our 1 over 5 out front. Do as much as you want to by hand. You can use a calculator as well. 4 cubed is 64, plus 2 times 4 squared, that's 32, minus, and then -1 cubed is -1, and then 2 times -1 squared is +2. Now we got 1 over 5. Just going to simplify this by hand the rest of the way. We got 64 plus 32 is 96, minus -1 plus 2 is +1, so it's just -1. And 96 minus 1 is 95. 95 times 1/5 equals 19. So what this is saying is that the average value of our function here, 3x squared plus 4x, on the interval -1 to 4 is 19. Right? And really, that's all there is to it. We'll have just an application type problem just so you can read one at the end. But if you think about this function representing the temperature, maybe in Celsius, from time equals -1, maybe that's like 11 p.m., -1, 0 being midnight, to 4 a.m., what it's telling you is on average, it is 19 degrees Celsius. Right. Number 2 says find the average value of the function f of x equals x cubed over x to the 4th plus 2 on the interval -1 to 1. Right, so pretty much want to set up the integral and then just see what happens. We're integrating from -1 to 1 of our function x cubed over x to the 4th plus 2 dx. And we have to divide by 1 over b minus a, 1 over 1 minus -1. Now, if you ever get tripped up, remember this number out here should be positive. So if you did it backwards by accident, you can just make that quick adjustment. That's why I always simplify that first before I do anything else. 1 minus -1 is 2, and I know I did it correctly. Now the question is, how do we integrate this? And it's probably been, oops, don't forget my dx. It has been a while since we've seen a substitution problem just because they weren't really popping up in the other applications, but it definitely is popping up in this one because we don't have a formula or a rule for integrating a fraction. That means we need substitution. And remember, sort of a default thing you want to go to is that if you have a fraction, unless if you have some typical or atypical setup, you usually want to try u equals the denominator first. So we're going to do u equals x to the fourth plus 2. Remember the other part of substitution, we do the differential, so we compute the derivative du. It's 4x cubed dx. And the way I do it, at least, is I solve for dx. We divide by 4x cubed on each side, and then we plug in. We're going to plug in what u is, which is right there. We're going to plug in for dx, du over 4x cubed. Remember, with definite integrals, you can also use the bounds to your advantage. So we could plug in for u, we could plug in -1 for x and figure that out. And then also the same thing for 1. Now I'm going to leave it alone for the time being. But you can do it like that, or you can change it back after you do the integration. So I'm going to do the change back thing. We have 1/2 -1 to 1. Remember, these are x values. So when we switch to u, we just have to remember that these are x bounds. We have x cubed over, this is what we made u, and then dx equals du over 4x cubed. Now we can see the x cubes are going to cancel out, which means we did it correctly. We definitely are comfortable with what we did. All the x's went away, so we probably made the correct substitution, and we did. Now I'm going to bring this 4 out because it's on the bottom, and when it comes out, it's going to be 1 over 2 times 4, which is 1 over 8. We integrate from -1 to 1, and we just have 1 over u du. Now, what is the antiderivative of 1 over u? Remember, these are x bounds, by the way. I said u, so I wanted to write u, but it's x. Well, the antiderivative of 1 over u is the natural log of the absolute value of u. And we want to plug in x equals -1 and x equals 1. Well, because we didn't switch our bounds, there's still an x. That means we need to convert back to u, to x from u. So we got 1 over 8 times the natural log of the absolute value of x to the fourth plus 2. Right, these are the absolute value bars, so it doesn't look like a 1. And it's plugging in from x equals -1 to x equals 1. 1 over 8, now plug in 1, subtract, then plug in x equals -1. And when we plug in x equals 1, we get 1 to the fourth, which is 1 plus 2 is 3 inside the natural log. Because it's positive, we can get rid of the absolute value. In fact, this is always positive, so you can get rid of it and make it a parentheses if you want. And then when we plug in -1, we get the natural log of -1 to the fourth, which is also 1 plus 2, which is 3. Now we don't know what the natural log of 3 is, but I do know that when you subtract something from itself, it's 0. So this is 1 over 8 times 0, which is 0. So that's telling you the average value of this function on this interval is 0, which is perfectly fine and acceptable. Right? It's a coincidence, but it is 0. Now this is a problem that I intentionally did not change the bounds, because if it changed the bounds, you actually would have gotten 0 much quicker. And I wanted to remind you of the absolute values and everything else. But if you changed the bounds, this is why I prefer changing the bounds, but I leave it up to you, whichever one you're comfortable with. If you had changed the bounds, so when we plug in x equals -1 and x equals 1 to u, we get u equals -1 to the fourth plus 2, which is 3. And then we also get, for x equals 1, you get u equals 1 to the fourth plus 2, which is 3. Well, why does that actually going to automatically make 0? Because when we plug in the bounds, in place of -1, we put 3. And plus of 1, we put 3. And then inside our integral, we had what was right here, but it's simplified to 1 over u. So I'll just make it 1 over u du. And these are u bounds. But the point is, it's the same bound. And one of the properties of integrals was that if you integrate from one bound to another and it's the same bound, it's always 0. So if you change the bounds and you get the same number twice, you don't have to go any further. You can just realize that it's always going to be 0. But once again, I wanted to purposefully go through this to remind you of the absolute value and the bounds, being careful that if you start with x and you don't switch, you got to write x just to remind yourself that we are using x bounds. But that's the main point. Right, now, this next one's actually a relatively accurate representation of the temperature of a temperature model of a location over the course of a day. It says in a certain city, the temperature in degrees Fahrenheit T hours after 9 a.m. So just keep in mind our starting time is 9 a.m. was modeled by the function capital T of T equals 42 plus 17 sine of pi T over 12. And we want to find the average temperature during the period from 9 a.m. to 9 p.m. Round your answer to the nearest whole number. All right, so why is it asking us to find the average temperature of just 12 hours and not actually 24 hours? Well, if you remember a lot from trig, it's that this 42 here is called the midline. And if you found the average over any full period, which would be 24 hours for a day, then your answer would be 42 because it's the midline. You're not really going to find an average temperature over the course of 24 hours because you don't have to actually use any calculus at all. You can use just trig. All right, so we have to be careful about our approach here. Well, we want to find the average temperature from 9 a.m. Well, that's our starting point, so T is 0. That's going to be my lower bound. To 9 p.m., which is 12 hours later. So T to 12. We have 1 over b minus a, which is 12 minus 0. So that's our ending minus our starting. And we want to integrate the function 42 plus 17 sine of pi t over 12. Right. Now, this problem is good for more than just an application. It's to remind you again, because it's been a couple of sections, but when we do substitution method, which we have to here, because it's not just t, you really need to break apart your integral into each part. So what I mean by that is we have this 1 over 12. You can leave it all the way out front and make two integrals, which is what I'm going to do. We integrate and we separate the integrate. So we have 42 dt from 0 to 12 plus, and then 17 sine of pi t over 12 dt from 0 to 12 as well. Now, the nice thing is we can integrate this one very easily because it's just a number, and this one we have to use substitution. We want to use u equals pi t over 12 because we need the inside to be just a letter. And when we do that, we get du. Since it's just t, it's going to be pi over 12, the number, dt. And we can solve for dt by multiplying by the reciprocal, 12 over pi. We know exactly what to plug in for dt. In here, you can also change your bounds on this one if you want. It's up to you. This one, there's no symmetry here, so it's not going to work out like the previous one because you're not going over 24 hours, you're going over 12 hours, but it's up to you. I still always like to switch the bounds, and I think it's a good practice, so I'm going to switch them. So at t, these are t values. At t equals 0, the u value, if we plug in t equals 0, we get 0. And at t equals 12, if you plug in 12 for t, you'll notice you get pi times 12 over 12, which is just pi. It actually makes our bounds a lot simpler. Right, so let's go ahead and integrate this thing now. We have 1 over 12 out front, big parentheses. We integrate the first part, we get 42t. And the bounds here are in t, so we got from t equals 0 to t equals 12. Then for the next one, we can bring this 17 out front. We have to integrate. Now we switch from u, it's u equals 0 to u equals pi. And then we have sine of u And then what is dt? We found dt was equal to du times 12 over pi. Right? It might look a little confusing, especially with one being the t bounds, one being the u bounds, but if you just do them separately, try not to look at both at the same time, then it's not too bad. We got 1 over 12. For the first one, we have 42, and then we plug in t equals 12. Oops, because it's just 42t. When we plug in t equals 12, we get 12 minus, and then plug in t equals 0, we get 0. All right, so that's from the first one, and then plus. And then for the next one, the 12 over pi, we also want to bring outside here along with the 17. Now the 12 over pi is being multiplied by 17. It might help just to do 12 times 17. And we get 12 times 17 is 204. So out front here, we're going to have 204 over pi. And we're left integrating just sine of u from u equals 0 to u equals pi. Right, so that's what we have left to integrate. And the other one we already integrated, we just need to simplify. We got 1 over 12 out front. Notice I kept that out front the entire time. Write a big parentheses here. 42 times 12 minus 0. Well, let's just do 42 times 12. 42 times 12 is 504. Let's go ahead and write that down. We got 504 plus, and then 2 over 4 pi, or 2 over 4 divided by pi. The antiderivative or integral of sine of u is negative cosine of u. So it's times negative cosine of u. And this is evaluated from u equals 0 to u equals pi. All right, and let's just continue here. So we got 1 over 12, big bracket. We have 5 over 4 in front, plus, but because I have a negative here, I'm actually going to just make this a minus 204 over pi. And then I want to plug in pi for cosine, or for u, and then subtract and plug in 0 for u. So I got parentheses cosine of pi minus cosine of 0. Actually, that should be a parentheses just to match the other one. Now, if you're unsure of that, just remember I took the negative sign here and I brought it out front with a 204. So it's just like a cosine of u plugged in pi minus plugged in 0. And then finally, we can finish up here. We got 1 over 12, 504 minus 204 over pi. Cosine of pi is negative 1 minus cosine of 0 is 1. So that's negative 1 minus 1 is negative 2. And we can add these together, or just pretty much, actually at this point, we've done enough. And we have to use a calculator to round to the nearest whole number anyway. So let's plug in our calculator. We got 1 divided by 12, parentheses, 504 minus 204 divided by pi times, I'm just going to make this negative 2 because it's negative 1 minus 1. And if you want to check, make sure it's typed in correctly. And actually, that one did not type it in correctly for us. So the negative 2 should be on the top, and it threw it on the bottom for me. I don't want that. Okay, let's see here. Oops. So let's go ahead and make sure it works. And that's what we want. That's much better. The negative 2 should be on the top or the side, not the bottom of the pi. And rounded to the nearest whole number, it's 53. So for the 12 hours after 9 a.m., from 9 a.m. to 9 p.m., it is 53 degrees Fahrenheit, rounded to the nearest whole number. Now, if you want to try to make sense of this number, you can. The one thing to just keep in mind is that it should be above 42 because, really think about what would happen during the 9 a.m. to 9 p.m. That's when the sun is up, so it should be warmer than the average, which makes sense. If you got something below 42, then we should be pretty alarmed because the average temperature at night when the sun's down should not be higher than the average. It should happen during the day. All right, so there's last little things. There's actually no problems here because it's kind of a weird theorem in my opinion, but it is one that in a very, very extreme case you might run into. So what I have here is there's no problems related to this, but it's called the mean value theorem for integrals. And all it says here is that if f is a continuous function on a to b, and the average value of f on the interval from a to b is k, then there exists a c such that c is between a and b, and f of c equals k. Now, what does all this mean? I'll actually use it within the example above. So for the example above, it said since the average temperature from 9 a.m. to 9 p.m. for, what was our letter here? It was T of T, capital T of T, which equals 42 plus 17 sine of pi t over 12. So that was our temperature function. And the average temperature from 9 a.m. to 9 p.m. for this function is 53 degrees Fahrenheit. It was rounded, but it's the intention of this problem is that it would have to be exactly this, but just pretend that I'm writing this decimal instead of this rounded number. What the mean value theorem says is that there is a time, there could be more than one, but there's at least one time between 9 a.m. and 9 p.m. when the temperature is 53 degrees. Fahrenheit, should add in Fahrenheit there. And you can actually graph the graph here to check it and understand that it works. So let's go ahead and just graph it real quickly. We have y equals 42 plus 17 sine of pi times t divided by 12. Right, and the temperature is between average at 42, so it's going to be way up here. And we want to look at the temperature from 0 to 12. So 0 is right here, and then 12 is right here. Well, 53 is right here, and you can see that roughly at 2.66, it does equal its average, pretty close at least. We can find its average because it's between 52 and 53 here, and the average is somewhere between it, so somewhere around 2.6. And it also hits the average again over here at around 9. But the point is that somewhere between time equals 0 and time equals 12, which is right here, the temperature is 53 degrees. Right? That's all this mean value theorem says, is that your function equals the average value of the function somewhere in your interval. But it has to be continuous. If it's not continuous, then it doesn't work. And the main reason it doesn't work is because you couldn't even integrate this, at least the way we know how to integrate. Right? But once again, this isn't a huge deal. The mean value theorem for integrals is just one of those things to point out. The main reason people would use it is they would say that this function, f of x equals x cubed over x to the fourth plus 2, has a root between -1 and 1 because the average value is 0. That's probably how most people would use, but ultimately it's not nearly as useful as the regular mean value theorem, so it's not used as often. But that is it for this section, and I'll see you in the next one.